Welcome back, everybody, and to week 43. So the topic this week, as you can see from the slides here, is to continue where we left last week about convolutional neural networks. And this is essentially the main method if you're dealing with imaging. And we are going to demystify some of the basic steps. So in case somebody would like to write their own code for a convolutional neural network, you should have the basic ingredients. And we are going to step through the kind of mathematics which is needed. And then we are going to look at the ways we are going to reduce the dimensionality of an image through filtering and through processes called like pooling, which we mentioned last week. And then how we can play around and set up a neural network with convolution, and how many parameters we end up dealing with, and so on and so on. You will see some of the mathematics which I brought up last week in connection with a simple example where we did a polynomial multiplication, but that was meant to illustrate the process of convolution. But we are going to use that one to actually show that the convolution itself can be rewritten in terms of a matrix times a vector, or matrix times a matrix, where the matrix is given by something which is called a band diagonal Toeplitz matrix. And that is a way by which you can efficiently implement some of the convolution steps. Now, convolution, as you see in this course, is something which we, when it comes to programming, for those of you who would like to apply that in project number 3, is something which we will limit ourselves in using something which is called Keras with TensorFlow. So Keras is an API. I don't know if everybody knows what an API is. I actually realized that last week. So an API is an application programming interface. And there is actually a Norwegian word for that, which I think sometimes is actually a little bit better. And I have to remind myself. So the Norwegian word is actually programmeringsgrensesnitt. And so Keras is an API to TensorFlow, which allows us to set up things in a very smooth way. And the thing which we are going to look at in the exercises here today, or the examples, is an implementation of Keras of convolutional neural networks. And if you're interested in dealing with this method in, let's say, project number 3, we don't expect that you may write a code using PyTorch or TensorFlow itself, but the basic approach is that to use Keras in implementing a convolutional neural network. Now, I also wanted to link to some material which you may find interesting if you want to dig deeper. We do have an own course on imaging and machine learning, so which actually uses the 2-3 first weeks to repeat what you have seen till now. So it's a kind of, if you have never done machine learning before, that kind of the first 3 weeks can be a kind of nightmare, because you will just have compressed everything we've done here in just 2 to 3 weeks. But then it moves on to convolutional neural networks and recurrent neural networks, which is going to be the topic now. So we have to be a little bit careful with not saying too much, because else you will get credit overlap. Okay, so there are some videos here which I normally recommend. And I've also stolen a little bit from these lectures at Stanford, which are really excellent. So this is something which is worth taking a look at. We also have the standard readings. And if you look into the textbook by Goodfellow, Benjo, and Corwill, if you wish to read a little bit more about the various technicalities, this is actually chapter 9 has an excellent description of convolutional neural networks. And I normally recommend looking at that. I will try to follow these lectures in order to demystify the different components or the different elements. And when you look at recurrent neural networks, or RNNs, then again, Goodfellow's chapter 10 is excellent. And I will also be stealing a lot from these lectures from Stanford. The textbook by Jérôme has many implementations, so it contains a lot of hands-on codes, but it doesn't talk so much about the different mathematical approaches which are behind the methods. And I'd also recommend to take a look, in particular in connection with project number 2. If you look at chapters 11 and 12 of the text of Benjo and et al., that contains a lot of these kind of practical hints and tips about you defining the parameters for a neural network. Which parameters should you tune first? Is that the learning rate, or the epochs, or the number of batches, and so on, or the hyperparameters? So there's a lot of practical kind of guidance in setting up a neural network. As we said in the very beginning of the neural network sessions, is that we do have the universal approximation theorem, which states that you can approximate a continuous function to a given error, but it doesn't say anything about the architecture, about the number of hidden layers, the number of neurons, the activation functions, etc., etc. These become parameters which we have to tune in order to get the best possible score. In our case, the score in project number 1 could be the accuracy, if you're doing classification, or it could be a mean squared error. Okay, so I'm going to switch a little bit back and forth between the slides and also the Jupyter notebooks and the whiteboard. But I just wanted to bring up this kind of general image or general setting of a convolutional neural network, and what are the basic ingredients. So let me just go back to go to the whiteboard. So let's set that one up. So if we look at the architecture and the options which we have now, and we set up a CNN. So this will be a CNN in a nutshell. So we have one main topic, which is the architecture. And that contains also a set of parameters. So we normally would then define what is called the convolution size. I'm just going to write conv for convolution. So this will be the number of convolutions we are dealing with, how we set up the filters. So this will be the filter. Remember now that we are using this filtering to reduce the dimensionality of an image. So if you have an image which is something like, has, let's say, 20 times 20 pixels plus 3 color channels, this will be an image which has 20 times 20 times 3 parameters if we are looking at a standard neural network. And what we are going to do now is actually to resize the shape of this image through the step of the mathematical process of convolution. So the convolution size is something which we need to define, and we need to define how many convolutional layers we have. And then we have other parameters which we are going to define a little bit. There's something which is called stride. There's something which is called padding. So these are all parameters. So they bring actually in a set of hyperparameters in the setup of a neural network. And then we're also looking at the depth, how many layers we want to have. Then we have something which is called the ReLU layer, or what we called last week the detection part. And this is another non-linearities. We have something which is called the pooling layer, which leads to a set of pooling methods. This is another way to reduce the dimensionality. And then we need to define something which is, obviously we have to have a definition of the number of layers, the width of the layers, etc. Then we have something which is called the flattening layer. So this is often a layer where we just flatten out in terms of just a long vector, all the data we have. And this is then fed into perhaps a fully connected neural network. So you have trimmed down the size of the image to a size which you can use a standard neural network with. So the next thing could be then a fully connected Then, if we now look at the next piece, so this is the architecture. And the architecture itself brings in a set of hyperparameters. So you could think of the number of, like in project number 2, you could think of the number of hidden layers as a parameter, a hyperparameter, the number of nodes, the width in each layer as a hyperparameter. And then obviously you have the activation functions, etc., which come in a given layer. And then finally, when we now move into the next piece, then we have the cost or loss function and optimization. So that brings in new parameters. So you would need to define the type of function, type of cost function, whether you're doing a classification problem or whether you're doing a regression problem, fitting a function. You need to decide what kind of regularization you wish to use. You need to opt for the gradient descent method. And then clearly you need to set up, if you're doing a stochastic gradient descent, I just write SGD, then you need to define batches and epochs. These are additional parameters. And what we have else is also other parameters which deal with the way we, for instance, want to reduce the gradients. If we realize that the gradient is exploding, there is something which is just called cutoff, where we just cut down the gradient and you go back to a smaller value, and then you keep iterating. And there are many such additional techniques. And if you take a look into chapters 11 and 12 of this textbook by Goodfellow et al., you will see a pretty good description of all these kind of practicalities. So many of these lack a serious mathematical foundation, but they're often inspired by your knowledge about the specificity of a given data set. Okay, so these are things which we normally need to deal with when we are setting up a neural network. Now, typically now the way this works, when we think of a CNN, so suppose now that we have a 32 times 32 image picture with the standard 3 color channels. So this could be an image which we are feeding in. And normally the way you would see this, so I'm actually gonna, I could have used the slides and showed you the figures, but I actually wanted to write them down here in order to just slow down things a little bit. So this could be your original image. So you would have a depth of 3. So this is your depth. You would have a width of 32 pixels. And then you would have a height of 32 pixels. So this is one way to think of an image which you are feeding into a neural network. And like you're doing in project number 2, we are dealing with the whole complexity, all the details, and they are multiplied with the weights, and they're fed into a hidden layer. And then we just continue with the full dimensionality. So we normally call this an affine transformation, where the weights connect all the input nodes with all the nodes in a hidden layer. And then we have a full connectivity between the different hidden layers. So a standard neural network is normally what we call a fully connected model. So what you typically would do then, when you look at this image, you would have some kind of filter which you apply to this. So we could write this one as a filter here. And this filter produces an image of a smaller size. So this could be, so you could have a filter. So this is the filter process. And this could be a filter, and now I'm going to define a little bit what this is doing. So I could have a 5 times 5 times 3 filter. So I'm keeping the color channels, and then I'm just making replicas of this image through the process of convolution. So let me try to explain to you what is going on when you're dealing with this kind of convolution process. So the filter is meant as a device to reduce the dimensionality of your images. Now, the thing is that this stage here, which is normally called the convolution stage, this produces an output where you now have reduced the dimensionality of the image. Now, what you could do is actually to have many such images of smaller dimensionality, and that is pretty common. So you're not limited to only have one image which you filter through, but you could actually have a series of these. And that will also define the depth of the output from the first convolution stage. Now, this is then sent into, so the output which you have here is then sent into what we normally call the ReLU stage. So we are going to set up the parameters here. So this contains parameters, which are weights and biases, plus these things which we call stride and padding and other quantities. So this contains several parameters which are fitted by backpropagation. Some of them are fixed by you and would have to be tuned in order to get the best possible reproduction of an image. But the parameters like the weights and the biases, they would be fitted by backpropagation. Then these quantities are then fed into a ReLU stage where you do a further filtering. So that produces a new output, a modulated one by the ReLU functions. That's pretty common in the setup of convolutional neural networks. Then after the ReLU stage, there is a new stage where you try to shrink the dimensionality further. And that's called the pooling stage. I'm coming back to what is the mathematics of the pooling stage. It's actually pretty simple. But the only thing we're going to set up now is that with this ReLU stage, this is the activation function, which receives the output from the convolution part. Then this brings into what's called the pooling stage, which is a further dimensionality reduction part. Now, these two stages, they normally don't have parameters which are tuned by backpropagation, but they have fixed parameters. If you think of the ReLU function, that has a parameter, so which you then would fix. You can replace that one with other activation functions. They would also have their own parameters, but these are things which you would fix before you run. And then you would train the weights and the biases which you get in the convolution stage by the backpropagation. Then you would have to, if you're not happy with the results, you can change the architecture, but you can also change some of the parameters which are called hyperparameters in the calculations here. So then you would have a pooling stage, and this is normally repeated many times. So what you see here now, these three pieces, so which we now could set up as something like this. So everything which we have here could now be written in as a big box. So we have the convolution or the filtering. And then we have this ReLU stage. And then we have this pooling stage. So this is normally called a convolutional stage. So you could say, I'm happy with just doing this one time, but this is something which typically is repeated several times in order to reduce the dimensionality of an image. So what you will typically see in most applications is a repeated usage of this convolution stage. So that means that you could have more of these. So you could have a new convolution stage because this produces an output. So suppose you start with an image which is a 200 times 200. by the first convolution stage, you could have reduced this to 100 times 100. And then you do a new convolution stage. So normally what is recommended is that you do several convolutions and that you don't make a huge reduction in just one convolution step, but you actually do this stepwise. So typically what you will see then is that you will have, this could be convolution stage 1, and then you could have a new stage, so which could be convolution stage 2, so just write conv here, and then you have a Relo stage, and then you have pooling here. So this could be your convolution stage 2, conv stage 2. And then you could just continue to the last convolution stage, and then you have an output of several series of convolutional stage. But a general convolutional stage contains these three processes. And these are the three processes which we are going to look at in more detail now. Then this output, which could normally be an image, if you have the three color channels, suppose you have reduced everything to an image of 50 times 50 times 3. Then you would flatten it out as just one long vector. So you would have a vector of length 50 times 50 times 3. And then that could be fed into a normal neural network. So in each convolution stage, when you do the filtering, you have parameters you need to train, weights and biases. So the convolution stage then is brought into some flattening. This is just a way to rewrite your output. And then this could enter a conventional neural network. And then you have the final output. And the final output is compared with your targets. And this feeds into your cost function. So this goes into the cost function, which then depends on your target, your output, y, your output, sorry, not that one, your output y, the target values, and the parameters theta which you have. And then you go back and repeat this a given number of times till your cost function has been reduced to a value which you could accept. And then you can then change the hyperparameters again, the number of layers, a number of convolutional stages, and so on and so on. But let's take a look at the convolution stage. So, and let's take a look at a simple example here, convolution stage. So let's suppose now that we are feeding in an image, and that image is now given by, or can just be a matrix. So what we are doing now is that we are feeding in some data, and I'm just putting letters here, A, B, C, D. This is not me trying to remember the alphabet. I, J, K, L. So this is the input. And in this input, we have what we have now is a matrix, which is a 3 by 3, 3 times 4. And then you could think of doing the convolution where you have a filter. So we have a filter here, which is now given by a 2 by 2 matrix. So we would have a width of our data, which is 3, and then we have a length or the height, which is equal to 4. And here we could now set up the filter, and we just give some values here, W, X, Y, and Z. So the filter is at 2 times 2. And what we are going to get then is actually an output, which is going to be of dimensionality 2 times 3. Now, there's a reason why I'm bringing up this simple example, because you will see that this kind of a convolution stage here with this filtering is going to represent well some of the parameters, but you will see that on the edges, if this was an image, there will be some of the values which are represented perhaps only once in the filtering. And that leads to hyperparameter, which is called padding. So that's one of the hyperparameters. Another thing which you're going to meet now is a new hyperparameter in the setup of this filtering process, and that's called the stride. So let's take a look at what these quantities mean. So if you take the filtering here, if we now look at the first one here, so we could take this guy here, this one, and this is going to give us one slot here, one of the cells. So I'm going to have A. So I'm now implementing the mathematics of the convolution. So if you look back at the equations we had last week, what I'm doing now is I'm taking this quantity here and multiplying with this one. Then I have this quantity with that one with that one, and this one with this one. So what I end up with now is this A times W plus B times X plus E times Y plus F times Z. So after we've done this exercise, I'm going to show you how you can rewrite this in terms of a matrix times a vector. And this is often the way this filtering is implemented in an efficient way in the computer. So let's just put some colors here. So we have this box here. Now, the next thing which I can do now is now to look at the next one. So I could take this one. This means that I'm using a hyperparameter, which is called the stride. And this stride is 1. So I just move, after I've done the convolution, I just move with one step. And you can see that I've done the move by one step, by just moving from A to B, and then I'm performing the convolution here. So what I'm going to get now is a new box, where I now have B times W plus C times X plus F times Y plus G times Z. So just using colors here. So this is a case where I now have a stride equal to 1. So this becomes a hyperparameter. So just let's keep this in mind. So when you're setting up the filtering, you actually have to define the stride. So when you use Keras or many of these softwares, it has as a default value the stride equal to 1. So now you see the way we would proceed. And so now I can actually really digress in usage of colors here. So this will be the next one. So let's just put up that one. So we would have now a C times W plus D times X plus G times Y plus H times Z. So that would be my next one. And then if we now continue like that, what we could have is to look at the next one. So we have a stride equal to 1. So that means that I'm now going down to this box and here. And I'm just going to repeat this operation. So I will get 3 new output boxes. And that means that in this particular case, I'm just going to write it down here. So we have now the next box gives me E times W plus F times X plus I times Y plus Y times Z. And this has now this green coloring. Then finally, I can now move on to the next one. I hope it doesn't look too messy. Let me just bring in this color. So now I'm going to have this one. So that's the next slot. So this is just a repeated usage of the convolution step. So I have f plus w plus g times x plus f times y plus k times z. So that is my second last one. And then I have the final one. So let's go back again. So the final one is now going to be given by this layer, or these slots here. And then we are multiplying with the filter variables. So that is the final one is going to give us g times w plus h times x plus k times y plus l times z. And then we have the final one. So the final image which we have produced now is a 2 times 3 image. So this is a way by which we now have reduced this image to a smaller image. Now, when we run this kind of filtering here, what we can do now is actually to set up a simple recipe by which we can find out what the dimensionality is going to be when we do this stepwise process. So if you look a little bit closer now, what we have, so a convolutional layer, what we would have then, the basic steps, we would accept a volume of, we have a width 1, we have a height of, for the first image which we take in, and then it can have a depth d1. So this will be the width, and then we have a height. And in case this is an image, we would typically have 3 color channels. And what we have is 4 hyperparameters in the setup here. One is k, and that is the number of filters. So we don't need, or rather, what is pretty common, if you have an image, you can actually make many copies of this image. So you can have many filters. So that means that if you have just one image of feeding in with 3 color channels, you can compress that to, let's say, 10 new images which have been filtered. And that would define the depth of the next inputs. So the number of filters becomes a hyperparameter. What you also need to set up is a parameter f, which is the spatial extent of the filter. So like the filter you saw here was a filter which had dimensionality 2 times 2. So that has a spatial extent of 2. So filters are always square things. That's a pretty standard. So the spatial extent of the filter, in the case which we had up here, we had a case which was a 3 by 4 times 1, which had just depth 1, and we had 3 rows and 4 columns. That's the example which we have. And then, if we look at the filter here, that has a spatial extent. In our case, this spatial extent was given by 2. So a 2 by 2. And then, we need to define something which is called a stride, S. And the stride was put equal to 1 here. And the stride is actually the way we are jumping in the filtering. So what we did here, if we run the 2 by 2 filter, and that obviously picked a box of 2 by 2 in the original image, and then it moved by just 1 step. But you can actually make this in terms of as many strides as you want, but the standard input is typically 1 to 2 strides. So the stride becomes a hyperparameter, which you need to tune. And we're going to see how we can implement that when we use Keras and the input variable. Yep.
If you were padding, right, you wouldn't lose the dimensionality, so would you then increase the stride?
Yeah, okay. That's pretty common actually. Yeah, that's pretty when you do padding. Yeah, that's correct. Okay, so the next thing is this padding, and this is something which we haven't discussed yet. So this is normally called the amount of zero padding. And we normally call this P, and in this case, it's actually put to 0. So we didn't do any padding here. Now, why is this interesting? Now let's go back to the convolution which we did. So suppose this is an image, and you have A, B, C, D, and so on. They represent different pixels. And now you're making a convolution of the image. And if you now look at what you have here, if you take a closer look at your convolution, you see now that the parameter A appears only here. So what happens is that the information about one of the corners appears in only one of the slots of the filtered image. So that means that this parameter A is less represented in the filtering process. You see, for instance, that something which is more in the middle, if you look at F here, this parameter, that pops up here, it pops up here, we have F here, we have F here. So in 4 of the filtered parts of the image, the information about F is present, whereas the corners are less present. So padding is a way to just add zeros around the corner. So let me show you, and now I'm going to steal some of the figures from these lectures from Stanford, which I think are excellent. So please feel free to take a look at them. So I should have them here. So let me just bring this up. So feel free, I've been snatching figures from this one. And there's actually a pretty good collection of lectures. And let me just bring up the padding issue. So you saw now from that simple example that we had a given corner which was not well represented when we did the output. So typically what you would do now is to have some kind of padding where you just add zeros to the corners. So this could be one padding layer, and we'll just add zeros. And this is a parameter which you then can add when you're using Keras or TensorFlow or any of these algorithms. So this is a way to actually improve the representation of the corners of the image. So this is like if you're doing modeling with periodic boundary conditions. I don't know if somebody has done that. With periodic boundary conditions, you always suffer from the fact that you have a finite box. And then clearly, if you have a huge box, the results will be less dependent on your boundary. But if you have a small box, there will always be a strong dependence on the boundary. So this is something which is pretty similar to a topic like periodic boundary conditions, which some of you may have met. So what you typically would do then is now to perform this padding. So you increase the dimensionality here, we'll just put zeros. And that means that when you now do the filtering, what you will see then is that these corners will be better represented in the filtered image. So padding becomes one of these variables which we have to deal with. So when you have these parameters, if we now go back to the whiteboard, and so we define a padding, and when we've done this filtering, this produces an output. There's a volume, so this will be the output of the convolution stage. So it produces a volume of size. So this will have a width, W2, a height, H2, and a depth, D2. In our case, the depth is just equal to 1. And this width is given by the width, the original one, which we fed in, minus F, the size of the filter, plus 2 times the padding parameter divided by the stride plus 1. And then we have the H2 here. So this would be the size of the new image, which is H1 minus F plus 2 times P divided by S plus 1. And then we have the depth, which is now simply given by the number of filters which we are applying. So in our case, if we now look at the example we had, so in the original example, what we had a W1 times H1 times D1, which was given by 3 times 4 times 1. And then we had a stride, S, equal to 1. We had a padding equal to 0. And then, if we now go back here, we also had a spatial extent of the filter, so F, which was equal to 2 here. So that means that when we do the mathematics, and with a number of kernels, K equal to 1, so this is a number of images we want to produce. You can actually produce many of these. So what we end up with then is an image where we have in total what we get then, when you do the math, you will see now there you have 3. If we do the math here, we would have 3 minus 2, which is 1, and then divided by 1 plus 1. So that gives us 2. That was the dimensionality which you see here. So we have 2 rows. And then we had a height of 4. So that produces now 4 minus 2. So that's 2 plus 0 divided by 1. So that becomes just 2 plus 1. So that's 3. So what we get then is that W2 times H2 times D2 is equal to 2 times 3 times 1. Now, what this also gives us is a set of parameters. So the number of parameters which we need, number of parameters, so because now the filter is connected with the input, and the connections then define the number of weights and biases which we need. So you will then see that the number of parameters, and we are going to look at that in an example a little bit later. So the number of parameters are then given by F times the depth 1 multiplied with the number of filters. And that's the total, these are the number of weights. And we need to add K biases. So in this specific case, what we have is a filter which will have dimensionality 2 times 2. D is equal to 1. So we have 2 times 2, and if we have just one filter, so we're going to have 4 weights which in the system plus 1 bias for the filter. So we are going to have, for this simple example, where we started with an image which was 3 times 4, and we filter it with a 2 by 2 filter. This is going to give us 4 weights plus 1 bias which we need to fit. So in this specific case, we are going to have 5 parameters which need to be tuned by the backpropagation algorithm. So in total, in our example, so this is going to be 2 times 2 plus 1 bias. So this is the bias. And this is equal to 5 parameters in total. Now, when you're doing this filtering, there's actually, and you will see that in some of the codes which we have, there are typical sizes of the filters which are very common to use. And these are the typical parameters for these hyperparameters. So typical hyperparameters. So this is just a collection which you will find used in many applications. So you have F, the size of the filter is a 3 times 3. You can have the stride, which is equal to 1, and padding equal to 1. So you put one layer of zeros. That's a typical set of parameters. Another set of parameters which is often used is to have a 5 by 5 filter. and then you would also have a stride equal to 1. In this case, you would often set P equal to 2, and I don't remember why. Then we have F equal 5. Now, remember now that not all of these fit when you do the stride and the padding. Because if you look at the calculations here, all the quantities which we want to have, W2, H2, and D2, we want them to be integers. Yeah?
Adding 2 and the stride on the 5 size kernel will give you the same size.
Good, good. I haven't thought of that. Thanks. Thanks. I actually haven't thought of that. Yeah. I've only been using stride equal to 1. Okay. So that's a good point. So and you see now that when you do this, you always have to look at the image you have and how many pixels you have, or what's the size of your input volume. And then you have to make sure that when you choose the stride, the padding, and the size of the filter, that when you then do the calculations here, when you set up these outputs, then you just have to make sure that you get integers. That's the main thing. So if you look at a typical application with s equal to 2 here, then what you would have is to actually figure out from the way the figure looks like. So I'm just going to put a question mark here. So in the output volume, the depth of the slice, that will be the result of performing a valid convolution of the filter over the input volume with a stride of S, and normally you would also have a bias parameter for every filter. So after the break, we are going to look a little bit more into some of the other technicalities like pooling, what that means, and how you typically do that. There's something which is called max pooling, which is a pretty standard choice. And this is a way to actually trim down the dimensionality of the output from the convolutional layer. And this can be fed into a new convolutional layer and a new layer, or it can just be flattened out immediately and then fed into a standard neural network, because then you have reduced the dimensionality enough. So like the MNIST data set, which we discussed in connection with the setup of a neural network, is already containing a set of images which is very much trimmed down. So we went from images which were 36 by 36 down to images the size of 8 times 8. So these are already very much trimmed down. And in that case, it's often sufficient with just one convolutional stage. I see I went a little bit over time. So let's just pause the recording. And so what we looked at before the break was a typical setup for the filtering. So let's just look at another example. So suppose we have an image which has 32 times 32 pixels, and it has the standard 3 color channels. And then we apply a 5 times 5 filter. And then let's see how we can reduce the dimensionality. So let's now just look at that specific example. So let's take a new example. So we have an image, which is, so the input image is an image with 32 times 32 pixels multiplied with 3. So it has 3 color channels. And then what we could apply then is something like, we could have 10 filters. So we're actually producing 10 scaled down images. So that means that this variable k, which we discussed, this hyperparameter is equal to 10. So this is something you can define in the architecture of the network. So you'd have a 10, you're producing 10 images, and then you have a filter, a 5 times 5 filter with a stride 1, s equal to 1, and padding equal to 0. Just to give you an example here. So that means that what you would get then is that the output volume, since this is an image which has the same weight and the same height, now the same width and the same height. Did I call it weight? Let me just test this. I actually suddenly got, yeah, it's width. I call it width. Sometimes I mix up width and weight. I don't know why. Okay. So the output in this case would be 32, and then we have -5, which is this variable f. If we just spool back here, we have the way we set up the width and the height would then be just the width of the original image minus the filters plus 2 times padding, which is 0 in this case. And then we have one stride. So this gives us 1 divided by 1 plus 1, and this is 28. And since we are dealing with 10 copies of this, then what we would have would be 28 times 28 times 10. So that would be the amount of images which we produce. So if we now include the channels, so if we now include the color channels, the 3 color channels, then the filter, if we now look at the filter, we have 5 times 5, so this is the size of the filter, times 3, plus 1, which is the bias. So this becomes equal to 76 parameters. And then we are actually producing 10 images here. So in total, we would have 76 times 10, which is equal to 760 parameters. Now, this image is then sent into this Relo layer, where it now produces a new output. And this is then fed into the pooling layer. So the Relo layer, when you're setting up your CNN, defines a new set of hyperparameters for you. And if you're using the ELU function, this exponential linear unit, you have additional parameters there. So these are parameters in the theory which you have to deal with, or in the architecture of your network. And then, when you've done this, so what you have here is actually 10 images, and then you can further process this. It's pretty common then to actually reduce the dimensionality of each image gradually through several convolutional layers. This is something you have to try out. So it's not given a priori how many such convolutional stages you need, but what's pretty common to do then is actually just to try. You would start with one convolutional stage, and then you repeat it, and just see if that improves your results. So the thing which we haven't looked at is actually this pooling stage. And I just wanted to say a little bit about what that actually means. So let's just look at the pooling stage, and I have to find my notes here. So the pooling stage. So what the pooling stage actually is doing is that it replaces the output of your net at a certain location with some kind of what we might call a kind of summary statistics. And there's a pretty standard way of doing that, which is something you would find as an option in basically all these kind of deep learning packages. And one of these is max pooling. So suppose now that so what this does actually, it reports the max output within a given region. And normally this is within a rectangular region. That's pretty common. Or rectangular neighborhood, which is actually a better word here. So just to give you an example, suppose now that we have produced these images, and then we have this detection stage or the Relo stage. This is something which comes out from the Relo function. And suppose now that we have 4 outputs here. And this is 1, 2, 3, and 4. And this could take a value, so let's just change color here. So this could take the value of 0.1, this has the value of 1, this takes the value of 0.2, and this takes the value of 0.1. So this is just something which I cooked up here. And then this is now something we want to feed to the next layer. And then there's this pooling stage. So what the pooling stage is doing now, when we are feeding this to the next stage, so suppose we just have 4 here. So there's also something which we didn't talk so much about. When you do this kind of convolutional processes, what happens is that you don't have a full connectivity. So that means that the first node you see 1 is not connected to all the 4 nodes which you have in the output. So this is normally just connected to some few ones. And that's one of the hallmarks of convolutional networks, is that you don't have a full connectivity, and that's the whole point, because else you're back to a neural network. So a neural network is a network where everything is fully connected. By the way, you actually have ways to reduce the dimensionality in a standard neural network by, for instance, just picking randomly only half of the nodes in a given hidden layer. So that's something which is often done as well in standard neural networks, and that reduces the dimensionality of the problem. So there are tons of such small tricks which are applied. So max pooling here, if we now look at the output, the kind of connectivity which you have is typically that this one feeds into only 2, since this is a corner, but then number 1 here feeds into that one, and feeds in here, and feeds in here. And then if we look at the next ones, so this 3 feeds into the 3 output ones. So this is a pretty common setup. And we have the final one, which now this number 4 here, which feeds in here. So clearly for those nodes which are at the end, there is less connectivity than for those which are not at the corners. Now what happens now is that we get as an output, we take the max value. So if you look at this specific node here, that receives 0.1 and 1. So that means that this just feeds out 1. Then what happens with the next one, so this will be 1 here, 2, 3, and 4. So the next one receives 0.2, 1, and 0.1. So that also feeds out 1. If I look at the next one here, I have 1 here. And then the final one has now 0.2 and 0.1. So that means that the final result is now given by 3 nodes which output 1 and 1 node which outputs 2. Now, what is often done is that you also have pooling with downsampling. So why should I keep 3 output nodes which give the same value? So I could actually downsample these 3 nodes with 1 to just 1. So this is also something which is applied, so it's called pooling with downsampling. So max pooling is often the standard choice, and this is actually the default if you use Keras. And then you can do downsampling. So that means that instead of keeping 3 nodes which give you 1, you just keep 1. So let me just mention that. So pooling with downsampling. And in that case, what you would actually be to shrink to less nodes when several neighboring nodes have same output. When several neighboring nodes, and then you need to decide neighboring nodes have same output, have same value. So the pooling stage is a way to reduce further the dimensionality of your images. And then this can be fed into a new convolution stage and a new convolution stage, and then you can continue till you're happy. And when you've done that, you would flatten out the results and then feed that one typically in either to an output layer directly, or you could just feed it through a standard neural network. So this is up to you how you actually want to set up your neural network here. So let's take a quick look at some images here. And let me bring back these slides from Stanford. So let me just, there's a typical image here which you will find if you look at the, this is a typical example. So you can see now in this kind of recognition of a type of object like a car, you can have a first convolution stage where you do the filtering. Then you can have a new ReLU stage where you produce the output with the ReLU function, activation function. So this becomes a parameter in your network, in your architecture. Then you can do a new convolution stage, and then you do a new ReLU stage. And then in between, you can have a pooling stage, so that actually disappeared from here. So let me just bring it down here. So you will see the pooling stage. Sorry for that, that disappeared. So these are the kind of ways you could actually do these kind of operations here. And it's pretty common also when you look at many of the setups here is to produce many types of outputs. So you could now think of having a sequence of such convolutional layers. So you can trim it down to a 28 times 28. You can have a new convolutional layer, so you can produce 10 images. And then you have a 24 by 24, and then you can proceed like that, on and on. So these are the typical ways by which you would set up a convolutional neural network. Now, there's one thing which I wanted to mention to you, which we went through last week, and I want to bring this up again, because this deals a little bit with the mathematics of a neural network. So let me now just find my slides. So one of the things which we looked at last time was a little bit about mathematics of convolution. And I wanted to rephrase this in terms of a matrix times a vector calculation, because this is actually the way you would implement these convolutional operations. So with the filtering, you could now think of doing this polynomial multiplication, which we discussed last week. And this is something which you normally rewrite in a more efficient way than just going head on and multiply S of t with the P of t. You would then perform an intermediate calculation here, and I actually forgot to change this once. And so this should be A0 times beta 1. Actually noted. So if you see that next week as well, then please reboot my goldfish memory. It needs constant reboots all the time. Sorry for that. Okay. And this is something which we could rewrite in terms of the convolution operation. Now, the thing is that this is often not that efficient to implement. So last week, I just brought this up as an example of the convolutional operation. But now I wanted to actually reuse this example to show you the way you mathematically would implement convolution as a matrix times a vector multiplication, which is very efficient from a computational point of view. So if you look at the operations here, you would typically simply sum here. The sum would run from minus infinity to plus infinity. You can obviously set limits here according to the number of such components you have in a polynomial. But what we could do is actually to rewrite, and convolution is a commutative process, so I can actually perform the calculations with alphas, with betas, or with betas times alphas. But you see now that when I rewrite this as a matrix times a vector calculation, this is something which can become much more compact. And I will show you how you can actually do that. That leads to something which are called cyclic matrices. In this particular case, especially if we have large images and a small filter, this multiplication is going to involve multiplications with sparse matrices. And this can be done very efficiently. And if you look at what we did here, you see now that you have a matrix with a kind of band tridiagonal structure. So these are normally called band tuplets matrices. That's one of the names you may encounter in the literature. But what we are going to get is something which looks more like a kind of cyclic matrix, which is going to be very sparse. But this example here serves more as a kind of way to motivate the way you actually implement the process of convolution. So the calculation which I did before the break of that simple 3x4 filtered by a 2x2 matrix or filter, this is something which I implemented with the equations which you see here, because you always have a discrete filter. You have a discrete set of data as inputs, and you have a discrete filter. So that means that the kind of continuous equation for convolution is something you never apply, but you always have a discretized problem. Now, if you look at this structure here, if we now go back to one of the examples we looked at before the break, let's take a closer look at that. And let's go back to the whiteboard before we then end the day by running some examples here. So let's take an example and see how we can actually perform the convolution stage. So let's suppose now we take a stride equal to 1, and we have a 2x2 filter, and we have an input matrix. So let me just write this out. So this is my input. So I have a I for input. So I01, and then I02. So this is a 3x3 matrix, which now contains, I should hurry up here because my pen is running out of battery. And then I11, and then I12, and then I have an I20, and I21, and I22. So this is the way my data could be represented. So if I have my image, each I here could be a pixel. And now this is convoluted, and I write it like this. So it's not a matrix multiplication, but it's a convolution. And then I have a matrix here with weights, W00, and W01, and W10, and W11. So if we now use the formula which we put up for the dimensionality of the image which comes out, this should be a 2x2. So we have 3 minus 2 divided by 1 stride plus 1 gives 2. So we should have a 2x2 output here. So the output is going to look like this. So we would have an I00. This is actually going to be exciting. So I don't do this on purpose to put you guys to sleep, but this is not perhaps the most exciting exercise we're going to do, but I just wanted to set it up here so you get a feeling of the mathematics of these methods. Plus I11 of W11. So we're going to have a 2x2 output here. So we have an I01, a W00, plus an I02, plus a W01, plus an I11, multiplied with WY10, plus I12, multiplied with that one. And then finally, let me just fill in the last slots here. 1, 0, 1, 0, 0. And then I have an I11, W00, plus I12, multiplied with W01, plus I21, W10 plus I22 multiplied with W11. So this is one way you can set this up. But what you could do now is rather to define a vector I prime, which now contains, this is the input, which has a length of 9. So I have 3 times 3 elements. So this vector I could now simply be, and this is a transpose of the vector. So this could contain I00, I01, I02, and now I just put up the final ones, I21 and I22. And this is just transpose. Then I can define a matrix, which I'm going to call for W prime here. And this is a matrix now, when I multiply that matrix, so actually my output is going to be given by this matrix, W prime, multiplied with this vector I prime. And that's going to give me the same type of output, except that now this matrix, which I'm going to set up, has dimensionality 4 times n. So I had a filter of 2 by 2, so that's 4. And then I have an input, which is 3 by 3, so that's 9. So I'm setting up a matrix which is going to contain lots of zeros. So this matrix is going to contain this weight, W's, and you can see that if you multiply it, and then it's going to contain W10 and W11, and then it's just going to have 0, 0, 0, 0. And then I can continue when I set up the next points, W00, W01, I'm going to have a 0, and then I'm going to have a W10, W11, and then I'm going to have 3 zeros here, 0, 0, 0. Then the next one, 0, 0, I think that's correct. So that should be 0, 0, 0, 1, and then I have 0, so 1, 2, 3, 4, 5, 6, and then there's another 0, and there's a W10, W11, and then the last one is lots of zeros here, and then I have a W00, W, I think this one has a 0 out here, and then I have a W01, and then there's a 0, 2, 3, 4, 5, 6, 7, right, so that should be correct. Now what you notice here is now that this repeats itself in a kind of cyclic way, and you have a kind of band structure here, and the rest of the elements are 0. So if I now implement this matrix as a kind of sparse matrix and perform the matrix vector multiplication, I'm going to get the same result as I would do if I implement the standard convolution operation. And this is from a computational point of view, is actually more efficient than doing the standard convolution process. So this matrix here, which you see is a kind of cyclic matrix, and you see that the matrix element just get repeated. These are the matrix elements or the weights. And you can easily set up such matrices and flatten out your input and then simply perform this matrix vector multiplication. And that's going to give you the same result as you had before. And you see now that if you do this, what you get, so you have a matrix which is 4 times 9, and you multiply a vector with dimensionality length n. So that means that it gives you out an output, a new vector, which has length 4. And when you did the operation here, this operation which you see here, that has 4 elements. So that means that you get out, instead of a matrix, you actually get out a vector which has 4 elements, and these are all the elements of this convolution operation. So this is a kind of technicality, and which you will see, and for those of you who may be interested in writing your own CNN code, I mean, feel free to do that. I mean, we don't require that because we don't want to have too much overlap with IN 5400, but this is a typical way by which you would implement the filters. Okay, so what I wanted to do now is actually to go back a little bit to the Jupyter notebooks and take a closer look at the way we would set things up with using Keras. So let's just bring this up. And there is an example down in the slides here where we use Keras. And one of the examples is this with the MNIST data, and that's not that interesting, but let's rerun it anyway. And just quickly remind you, so this is a data set. And in this particular case, as we discussed last time, we import the types of layers which we're going to need, the types of regularizers, the types of optimizers, and then the output here, which is going to be given by different classes. And then we do the standard test train splitting. So nothing particular here, but these are just initializations of the API, the Programmeringsgrenzetversnitt, Norwegian word, which I think is actually a better word than API. And the way you will set it up now, you set up the different convolutional layers. We are going to look at an example now where we're going to be a little bit more specific, where we can actually set up the number of outputs we want to have, the number of images which we want to produce. But you see now, this is the pool size, this is your filter. So this parameter F, which we defined in the previous lecture, this is now set to 2. So this is a 2 by 2. And if you don't say anything about max pooling, if you don't say anything about the stride and the padding, then it just takes the default values for the stride, which is normally 1. But you would have to look up the parameters for that. I always have to look up because I don't remember what all the parameters are. That's often the problem when you use the software written by other people. And here, you see now you do the pooling layers, you have the convolutional layer, so this is the filtering. You flatten it out, you feed this into a dense neural network, and then you have the standard parameters here with epochs, the batch sizes, the number of filters, the receptive fields, which we discussed before the break, the number of connected neurons, which you then use in the standard connected layer, and the number of categories, which is actually your output layer, where you have an activation function, which is the softmax. And then you can run this over the hyperparameters. So you will typically start with a value for the learning rate, which in this case span from 10 to the minus 5 to 10 to the power of 1 on the log scale, and the same with the lambda values. And you would then run over these parameters, learning rates and the hyperparameter, and then simply produce the output and then visualize the output. But the thing I wanted to show you now is another data set, which is called the CFA data set. And by some odd reason, I have a character here which pops up every time I regenerate the file. So this data set produces this kind of images. So it's a popular data set which contains something like 60,000 images. Now, the big data sets, they contain millions of images, and they are really trained to specific features. One thing you need to keep in mind when you're looking at convolutional neural networks, that they are really trained to specific types of images. So if you want to classify animals, or you want to classify houses and so on, you actually have specific training where you look at filters which take specific features. So this is something you have to keep in mind, that many of these data sets like ImageNet or other ones, they're really tuned, and the filters are tuned to specific sets of images. So in this data set, you have something like 60,000 images in 10 classes, and then you have 6,000 roughly in each class, and then you will divide it in 50,000 training and 10,000 test images. And then these are typically the quality of the kind of images you get and the type of images: birds, cats, cars. There's no bike here. No bike. That's disappointing. I hate cars. Sorry. No, I don't hate cars. I mean, that's wrong to say that. I would like to reduce the number of cars considerably if I were to decide. Okay. Anyway, so you would set up the model then. And now you can see, if you set up the model here, if you look at the first one, so what we are doing now is to do a filter, 3 by 3 filter, and we are producing 32 images. So this is the 32 here. So the basic size is 32 times 32. And this is your input shape. And what we are doing now, if you look at this, there's actually a model summary, which is very useful. And you will see now that you have 896. And if I did the math correctly here, so what you have a filter which is 3 by 3, and then you have 3 color channels. So that gives you 3 by 3 times 3, it's 27, plus 1 bias for the filter. So that's 27. No, sorry, 28. And then you make 32. So if you take 28 times 32, that gives you 896 parameters. So this is the set of parameters you see from the first convolution stage here. And then there's a pooling stage. And in the pooling stage, you don't have any hyperparameters. That is fixed. So that means that you will actually have to rerun it with different types of pooling stages. So the parameter training takes place in where the backpropagation kicks in is in the convolutional stages. And then here you would produce 64 images. So you have downscaled this image, and you see now the downscaling becomes a 30 times 30 sized image. So you went from 32 times 32 to 30 times 30, and you make 32 images by the filtering. Then you do a new, so the pooling stage now actually reduces this to 15, 15, and then you have 32. So the pooling stage has actually reduced by a factor of 2 the size of the width and the height. And then you can do a new convolutional layer, and in this case we produce 64, but we do a downsizing again by a filter, 3 times 3, and then you can see that you have 15 minus 3, there's 0 padding, divide by 1, plus 1, and that gives you 13. So that gives you, no, I think there's a padding here. So that gives you 13 times 13 and 64 images. And then you have a new pooling stage, and you reduce the dimensionality further. In this case, there are no parameters. And then you have the final stage where you have reduced everything to a 4 by 4 image. So this is basically the setup of the network, which so this is something you could actually set up and play around with different parameters. So the most important thing is that you actually understand what these parameters stand for. And then if we go back to where we started in the beginning of the lecture, and you look at these different parameters you can set up here, if you now go back to where we were in the beginning, so let me just bring that back, what we wrote down in the very beginning. Sometimes, here it comes. It takes some time sometimes. I don't know why. If you look at the architecture, so we have now the convolution size, the filter. So that is a parameter we have to choose. We need to define parameters like the stride, the padding, and the depth. So these are all parameters which enter into these Keras functionality. We need to define the activation stage, or the detector stage as it's called. And there you can change the ReLU to ELO or leaky ReLU or other types of activation functions. You need to define the kind of pooling methods you want to deal with. And then you have a flattening layer, and then you have a fully connected layer. You saw the last example, we didn't do anything of that. So we would just feed that one into the final output function. So there was no flattening, and there was no kind of final neural network stage. So these become all, so the padding, the stride, the way you do the pooling, these all becomes hyperparameters in the setup of a convolutional neural network. And then you need to define the type of cost function you want to deal with, the type of regularization, the type of gradient method, and also whether you want to do a stochastic gradient descent or just a plain gradient descent with momentum, plain gradient descent with adaptive learning rates with ADA-grab or RMS prop or ADAM or other methods. So there's so many parameters at a certain point you actually get overwhelmed. So let's go back and try to finish or wrap up today by looking at this example on this specific data set. So this is actually very useful to look at. So if we want now, if you look at what we had here, now this could be the convolutional stage. So what you could do next then is actually to flatten it out, and then you could add a dense layer. And you could have an activation function, which again is a rel function if you want to. So we, oops. And then here, you can now count the new parameters. So you see now in the beginning, I had the convolutional stages and the pooling stages. And then I flatten out, there is no hyperparameter there. And then I'm just feeding these in to the dense layer. And here you see the number of weights and biases I need to train. And then I have 10 categories, which I want to classify. So that gives me 10 outputs. So whether it's a bird, or car, or truck, or whatever. And we have 10 categories. And in this case, we have 650 parameters. Because we have 10 biases plus 64 times 10. So these are the number of weights in a standard neural network. So that gives us 650 here. And the total parameters you need to train then, in this case, is a little bit more than 100,000. So clearly this is it's still a small case, but it's actually much, much more than what we were used to in project number 1. And then we can compile and run the model. And this is just going to take a little bit of time. There's no need to, you can actually run it yourself if you want to. This is actually going to take some time. And the accuracy, when you look at the accuracy here, you will not be impressed, actually. It's not. You would have to fine-tune this network much more than what I did here. So this is the way I read convolutional neural networks, is as a way to reduce the dimensionality by the process of convolution. And you would repeat this again and again, because you have images of huge sizes, and normally you train millions of images. So this kind of activity is a very it's a very active research field, and it's being applied to tons of different disciplines in natural science, but not only natural science. You would have it in psychology, you would have it in brain research, you have it in physics, where you're looking at the output from experiments, and you can have traces in your detectors, which you can recognize as images with lots of noise, and you can train the image recognition with a CNN. That's pretty common. But the downscaling of the images is also something which is very important. And often you have tons of data. So you actually need to do some filtering out of the tons of data before you apply one of these methods. So if you're interested in these activities, you have something like this course, which we call IN 5400. And they actually dive more into the gritty-nitty details. And you actually end up writing a code for a convolutional neural network, which is not something we will do here. I mean, we're not going to ask you, but clearly if you want to do it, I mean, there's nothing which hinders you. So the basic mathematics and the basic things you need to code are the things which we have exposed here. So I hope you see the more overarching philosophy without us going into the details of writing a code like we did with a neural network. But the most important thing for us is to see what enters a convolutional neural network. And I hope this lecture has been able to expose it, and then that this triggers some interest in perhaps following IN 5400, which is a very good course, actually. And Anne Solberg, who teaches it, does an excellent job. So tomorrow, we are going to look at another type of deep learning methods, which is very relevant for studies of, for instance, time series. And these are called recurrent neural networks. And that is going to conclude the deep learning part of this course. And then we're going to move into other machine learning methods like decision trees, random forests, gradient boosting, and other techniques. And then next week, we have only 4 weeks left of the semester. Sadly. Yeah, time flies. Okay, guys. Thanks for coming, and have a good afternoon. Eh? Thanks.